Here we are to verify whether the given set, in this case the set of positive rational numbers, is a group under the binary operation star defined as a star b is equal to the product of ab all over 2. Here we are already sure that it's a binary operation. Take note that for it to be a binary operation, of course, first and foremost, it should be non-empty. And we know that the set of positive rational numbers is non-empty and that it is closed under the operation. We will not be checking whether it's closed under the given operation because it is already given that it's a binary operation. However, we are going to focus on the identification whether this set under the operation defined, that 8 star b is equal to ab over 2, is a group. For that to happen, we need to satisfy 3 conditions. Let's coin them G sub 1, G sub 2, and G sub 3. So for G sub 1, we need to establish that star is, or the operation star, is associative in Q plus, or the set of positive rational numbers. And if we can do that, then of course we will proceed to G2 or G sub 2. It depends on how you're going to call it, since I already labeled it G1, so let's have it G2 and G3 later. So to show, we need to establish that the idea of associativity will hold such like this: the grouping of A star B equals star C rather equal to A star the grouping of B star C. So we are going to let here A, B, and C element of Q plus, so that we could apply it here. So of course, let me use this again for our left hand side. Let's start with our left hand side. When we have A star B, it's already given that this is equal to A, B, or the product of the 2 elements over 2. Okay, but that is still to be subjected to star C. And we are going to treat this as one element as we move further. The next part here is if this would be our A, so we'll be multiplying this with B, which is the second. So you have A, B over 2 times C, which will be having a denominator of 2 here as well. Okay, so with that, we are going to simplify this. Of course, the C can be written as C over 1, so you will have your numerator ABC over 2 all over 2. Using the keep change flip method, because we know this is 2 over 1, we have here A BC over 2 times 1/2. This would mean that our left hand side is ABC over 4. Let us find out if we will have the same expression using the right portion of the associative property. That means A star B star C in this manner. So B star C is BC over 2 because we are multiplying the elements all over 2, but this will be subjected with A star B. Following the same idea, so we're going to multiply the 2 elements. This will be treated as 1. So A times BC over 2, and the product will still be divided by 2 because we have here a constant 2. This would mean A over 1, so you have ABC over 2 all over 2, which is almost already the same as this here. But to simplify it further, this is 2 over 1, you have ABC over 2, sorry, that's 2, times 1/2, which will give us ABC over 4. Both results are the same. Hence, we can say here that star is associative. Now that we have established that star is associative, we are going to proceed with G2. Let me use other color here because we will be using the spaces at the bottom here. So G2. What does this G2? The G2 means, or the content of G2 is that there exists identity element on the set that will satisfy a certain equation. So if we're going to have here, sorry for that. If we're going to have here, let any A element of Q plus, okay, we are going to find a certain E, which is also element on Q plus such that we could satisfy this equation. A star E is equal to E star A is just A itself. This E, okay? This E should be for all, pardon again, this E should be true for all A element of Q plus. It should not be true for only one or a few, but it should all be true for all. So what would be the element of E here? Let's try to look at this algebraically. If we have A star E, and following the definition earlier that A star B is AB over 2, I'm copying it here so that we will not be going back to the top. This is just equal to A E over 2. Okay? That is its equivalent value. The other side, E star A, should also follow the same condition, EA over 2. But of course, since this is under multiplication, we can rewrite it because that's usual multiplication is commutative, AE over 2. So you have the same results, and we are going to look for E. And what would be that certain E? Let's since we have the same result here, let's just equate one of them to our A here. So since A can be found on both sides, we can multiply both sides by 1 over A. 1 over A. That's 1. So we have here E over 2 is equal to 1. Then multiplying both sides by 2, you will have here E is equal to 2. Now, is 2 element of Q plus? Take note that Q plus is a set of positive rational numbers and 2 is a rational number. Hence, we have established a certain identity element for this, and the identity element for this situation is 2. And since again it's an element of R, we have satisfied G2. Okay? Because what we would like is to find a certain value for E that is still part of the same set. We did this algebraically because we have here a situation equating to A. Okay? That's for G2. Let's proceed to the last condition, which is G3. Take it again that the operations A star B equal to AB over 2. So what is G3? For G3, we need to show here, we're going to let a certain inverse element of Q plus. Okay? Certain element of Q plus. And we're going to find, let's do it again. That's A. We're going to find A inverse still element of Q plus, meaning G3 is all about existence of an inverse element. Okay, such that following the definition, A star A inverse is equal to A inverse times A, which is equal to E, that is 2. Okay, if we could establish this, but of course our inverse here is unique for each element of A. Okay, for all A element of Q plus. Okay, so we're going to find certain representation for the inverse because we're going to use their algebraic forms because our set is infinite set, the set of positive rational numbers. You cannot have specific inverses for each of the elements of the same of the said set. So if we're going to follow A star A inverse, this would follow that A inverse over 2, right? As the product there. That would mean if we're going to use the same thing the other side as well, you will have A inverse A over 2. And since again this is commutative, you have A inverse A over 2 and they are the same. So what would be the representation of our inverse? Take note that this should be equal to E. So A inverse times A, or we will have the representation already, the result here. This should be A. Yeah, A times A inverse is equal to 2. Over 2 must be equal to E, which is 2. So what would be the representation of our A inverse? Cutting this out, you will have here A inverse over 2 equal to 2. Multiplying 2 both sides, you will have here a form. Let me write here, or I still have I don't have much spaces now. So you have A inverse is equal to 4. Dividing both sides by A, our A inverse, okay, must be represented as 4 over A. Is 4 over A element of Q plus? That's a big question right now, because if yes, then we have satisfied G3. Take note that our A here is any element of Q plus. It could be a positive integer, a positive fraction. Okay? And if we're going to substitute our A here, our result will still be a rational number. And this is correct. Therefore, G3 is satisfied as well. Okay? Again, we cannot give an exact value. We just use representation because our set is an infinite set. So with G3 satisfied, G2 satisfied, and G1 satisfied, since star is associative, we can say that Q plus, let me go back to my, to my first caller. We can say that Q plus under star, which is definition, is a group. Why? Because we have satisfied the 3 conditions. And that is how we verify whether a set is a group under a specific binary operation. G1, associativity, G2, existence of an identity element, and G3, existence of an inverse element. Thank you very much for watching.